I look at the newest image of 3I/ATLAS captured on November 20th, and the first thing that strikes me is how mercilessly it tears through every rule we thought we understood about comet physics. No warm-up, no gentle prelude. What you're seeing is a direct challenge to the foundations of how gas, dust, rotation, sunlight, and gravity behave in interstellar visitors. The object doesn't politely bend to our models. It slices right through them with two impossibly straight, razor-thin beams, stretching nearly 1,000,000 kilometers into deep space. As I examine these features, I realize that if they're real, and the data shows they are, then something extraordinary is happening. Something that forces even seasoned astronomers to pause mid-sentence and question every assumption they have about natural comet morphology. These straight lines, they don't curl, they don't twist. They don't feather outward like traditional cometary jets. They stand rigid, vertical strokes on a sheet of black cosmic paper, defying the expected chaos of a rotating, outgassing body. And that's the first rupture with tradition. 3I/ATLAS spins once every 16 hours. That's fast enough that any plume of vapor or dust bursting from the surface should be whipped into a curved arc. Centrifugal force should dominate. Gas expansion should push outward unevenly. Rotation should distort everything. But instead of curling like every jet we've ever modeled, these two lines remain as straight as a laser level, extending across hundreds of thousands of kilometers with no measurable deviation. At this scale, even minuscule forces amplify into sweeping distortions, yet these lines never budge. When I zoom in, I feel the almost uncomfortable sensation of looking at something that simply should not exist in the natural universe. A comet, even an interstellar one, should behave like a misbehaving sprinkler, spinning, sputtering, coughing out dust in chaotic, spiraling patterns. But here, 3I/ATLAS stands like an artist who refuses randomness, drawing instead two perfect strokes that intersect the ordinary comet tail, forming what looks eerily like a cosmic X, an X drawn with intention, not accident. Every instinct trained from decades of studying astrophysics tells me jets cannot be this straight. Every simulation we've ever built tells me rotation must break the lines. When physics and observation collide this violently, something fundamental is missing from our understanding. But the challenge doesn't stop at shape. The orientation of these cosmic beams detonates a second shock wave through comet theory. Comet tails and jets always point away from the sun. This is not a preference, it's a physical law. Solar radiation pressure and the solar wind blast particles outward, aligning the dust and gas along a predictable axis. Whether the comet is calm or hyperactive, slow or fast, small or massive, the direction of the tail remains faithful to the sun object line. And yet 3I/ATLAS has the audacity to ignore this law completely. The two narrow beams don't point away from the sun at all. They sit perpendicular to the expected axis, as if the sun's influence were nothing more than a gentle suggestion they chose to disregard. Imagine blowing on dandelion seeds and watching some of them hover motionless sideways instead of drifting away from your breath. That is how absurd this alignment is. No natural mechanism we know of, no outgassing geometry, no internal fracture, no pressure gradient, can launch particles sideways at such scale and maintain that orientation across 1,000,000 kilometers. And if these beams are not dust but fragments, solid objects flung into space, then the required ejection speed would be around 500 meters per second. That's nearly twice the muzzle velocity of a handgun, and not in a random direction, but in a perfectly consistent sideways trajectory that ignores the sun's dominance. This is the moment where science begins to sweat. Astronomers have tried to salvage natural explanations. Maybe giant slabs of ice cracked and shot into space. Maybe a complex rotational resonance is locking the jets into place. Maybe the comet fragmented just right. But each attempt collapses under the same weight. Rotation should bend the beams. Sunlight should push them away. Dust should diffuse. Gas should arc. Nothing wants to stay straight. Nothing wants to remain sideways. For a natural mechanism to produce this, the conditions would need to be so exquisitely fine-tuned that they border on miraculous. And scientists, by nature, distrust miracles. Which opens the door, not to conclusion, but to possibility. Avi Loeb from Harvard has suggested that the straightness, the length, the unnatural perpendicular orientation might fit something entirely different, objects deliberately released, perhaps from a larger parent body, moving with intentional velocity rather than chaotic outgassing. If you take the data at face value, these lines behave less like cometary jets and more like controlled trajectories, paths you'd expect from small probes, sensors, or debris separating from a central craft. I'm not saying that's what they are, but I am saying that when nature behaves this unnaturally, we are obligated to consider every hypothesis, even the ones that make us uncomfortable. In my analysis, 3I/ATLAS delivers a clear message. Our comet physics is incomplete. Something is happening out there that our equations cannot easily explain. And that's why this discovery matters. Because every time the universe breaks one of our rules, it is an invitation. An invitation to rethink, to explore, to question the assumptions we cling to. This interstellar visitor is not merely passing through our solar system, it is passing through the very boundary between known physics and the unknown. And in that boundary lies the frontier of discovery, where doubt becomes curiosity and curiosity becomes revolution. If these beams disperse, fine. It's a comet obeying unfamiliar but natural behavior. But if they hold, if they accelerate, if they align with trajectories rather than solar wind, then we will have to confront the possibility that 3I/ATLAS is not just an icy rock drifting between stars, but a message carved into the fabric of space, challenging us to acknowledge that the universe may be far stranger and perhaps far more inhabited than we dared to imagine. When I revisit the data the next morning, I find myself staring at the same contradiction. A natural body exhibiting behavior that refuses to act natural. And the deeper I go into the physics, the more 3I/ATLAS begins to feel like a riddle written in a language our textbooks haven't learned yet. I start dissecting the problem from the ground up. Mass, rotation, thrust, solar pressure, hoping that somewhere, hidden between the equations, a subtle oversight will restore sanity. But the opposite happens. Every parameter I examine pushes the object further away from the realm of ordinary comets and deeper into a category with no name. The two beams are not flukes. They are features, consistent and intentional in their geometry. The first question I ask myself is brutally simple. How does a rotating body maintain straight jets? If the surface vents gas, that gas should arc. If fragments are ejected, they should drift into curved paths, pulled and twisted by the object's spin. Even a small angular velocity imposes a spiraling trajectory. But with 3I/ATLAS, rotation seems irrelevant. It spins every 16 hours, a substantial speed for an object only a few hundred meters across. Yet nothing bends, nothing curves. The beams extend like rigid scaffolding pressed into the night. Imagine a figure skater spinning rapidly with firecrackers strapped to her arms. The sparks would swirl outward in a glowing spiral, but 3I/ATLAS, its sparks refuse to follow the dance. They behave as if the spin isn't there at all. I try to imagine what natural mechanism could exert such control. Pressure locking? Jet collimation by magnetic fields? But magnetic collimation requires strength far beyond what a small icy body could produce. The magnetic fields of comets are weak, barely detectable. They cannot sculpt million-kilometer beams. Gas collimation only works for a few kilometers before diffusion spreads it. Dust is even less obedient, scattering widely. Yet these beams are so thin, you could trace them like graphite strokes on black velvet. That level of precision, sustained over such distance, is more reminiscent of engineered emission than chaotic outgassing. And even as I resist the comparison, my mind keeps returning to structures we've built: ion trails, plasma plumes, controlled exhaust patterns. But shape is merely one violation. Orientation is the rebellion that truly unsettles the astrophysics community. Again, I return to first principles. Sunlight exerts pressure. It pushes dust and gas away. It shapes the tail. For billions of years, comets have obeyed this rule without protest. Their tails point away from the sun like compass needles aligning to a magnetic field. Yet 3I/ATLAS positions its beams almost perpendicular to that direction, as if defiantly ignoring the solar wind that should dominate their dynamics. I visualize the position: the sun to the left, the comet moving forward, its natural dust tail stretching backward. And then, like an impossible afterthought, two beams slicing horizontally across this arrangement, unbothered, unmoved. For those beams to remain stable, they must be composed of something with enough mass or velocity to resist solar pressure. But to maintain that level of stability across 1,000,000 kilometers, the required ejection velocity approaches 500 meters per second. This is no gentle puff of sublimating ice. This is a cannon shot. And it doesn't point away from the sun. It points sideways, like a deliberate maneuver. The word maneuver echoes in my mind longer than I'd like to admit. In natural systems, randomness wins. In artificial systems, trajectory wins. And 3I/ATLAS behaves much more like the second than the first. Astronomers have proposed fragment ejection, chunks of rock breaking off after thermal stress. But if such fragments were expelled, their paths should diverge wildly. They should tumble, arc, scatter. Instead, they form a line so surgically straight that even skeptics in the field are forced to admit something is deeply wrong with the natural explanation. I read the debates, heated exchanges between those insisting on conventional physics and those arguing the observations demand broader thinking. The tension is palpable. Some cling to tradition like a lifeline, afraid that acknowledging the anomaly opens the door to speculation they consider dangerous. Others whisper what they're not yet ready to say out loud, that maybe we're witnessing something fundamentally non-random. And that's when Avi Loeb steps into the room, not physically but conceptually. His argument is simple. If it behaves like controlled motion, why dismiss the idea that it might be controlled motion? Not proof, not conclusion, just possibility. I find myself agreeing with his premise even if I withhold the final step. Science does not advance by ignoring the uncomfortable. If 3I/ATLAS had produced curved jets, aligned tails, diffuse dust plumes, this conversation wouldn't exist. But it didn't. It produced geometry that looks almost architectural. I consider the implications. If these beams are objects, independent bodies, then their mass, velocity, and persistence must be measurable. A natural fragment should slow, scatter, fade. A controlled object might accelerate subtly, maintain coherence, follow a trajectory. The next observations will decide which branch of physics we must prune and which we must cultivate. If the beams disperse, comet physics survives intact. If they don't, the ramifications extend far beyond astronomy. As I sift through the data, a strange feeling washes over me. Not fear, not excitement. Something more solemn. A sense that we are witnessing the universe tapping our shoulder, asking if we're still paying attention. And I realize that this is the true value of 3I/ATLAS. It forces us to admit that the cosmos still holds surprises capable of humbling even the most confident scientist. That there are still frontiers where our models collapse and our curiosity must carry us forward. And as I close the data set for the night, I know this anomaly is no longer just a scientific event. It is a crossroads, a moment where the universe presents us with lines drawn too straight, too bold, too deliberate to ignore. Whether nature is playing a trick on us or offering a clue to something greater, the only honest response is to keep looking, keep measuring, and keep questioning everything we thought we knew. When the next set of observations comes in, I immediately look for decay. any sign that the beams are fading, widening, or bending under the relentless forces of the solar wind. Natural jets weaken, natural fragments disperse, natural dust clouds unravel, but the lines emerging from 3I/ATLAS refuse to behave like anything natural. They remain unnervingly straight. Their edges stay unnervingly sharp. And as I scroll through the data frame by frame, an unsettling realization forms. These structures possess coherence. Coherence is a word we reserve for systems with organization, not chaos. And yet here it is, etched across millions of kilometers of space. I dig into the trajectory of the beams, plotting their angle relative to the Sun-Comet axis. If sunlight were influencing them even slightly, I would expect measurable drift. But no drift appears. Their orientation remains locked, almost as if tethered to an internal reference frame rather than responding to external forces. I imagine a weather vane refusing to point into the wind. You'd know instantly that something invisible was steering it. That is exactly how these beams feel, steered, held in place by a mechanism we cannot identify. Meanwhile, the tension in the astrophysics community is reaching a boiling point. In private emails and conference threads, you can see the divide widening. On one side, the traditionalists insist on patching the Comet model, adding layer after layer of increasingly improbable assumptions. Maybe the fragment ejection was extraordinarily precise. Maybe the dust particles interlocked. Maybe rotation slowed temporarily. But each maybe outweighs the last, until the theory resembles scaffolding built from wishes rather than evidence. On the other side are the scientists who feel the weight of the anomaly pressing down on them, forcing them to confront what the data is screaming. This object is not playing by the rules. And whether they say it out loud or not, every one of them is thinking the same forbidden thought. If this behavior is not natural, then what kind of system could produce it? I'm not ready to make that leap, but I am ready to ask the right questions. I return to the physics. If the beams are composed of dust, the particles would need extraordinary charge or mass-to-area ratios to resist solar radiation pressure. If they're gas, they would require confinement far beyond what a fractured, icy core could provide. If they're solid fragments, they must move with nearly identical velocities, within centimeters per second of each other, to maintain such radial precision. That degree of uniformity is vanishingly rare in natural ejecta. It is, however, exactly what you'd expect from engineered deployment, where synchronization is a feature, not a coincidence. But I push that thought aside for now. Instead, I test the idea of internal structure. Could 3I/ATLAS have a rigid spine or cracked plane that channels emissions with unnatural sharpness? But the object is too small for such structural complexity. And even if it existed, rotation would still twist the jets. Nothing eliminates that problem. The comet is spinning. The beams are not. This is the heart of the anomaly. The next observation reveals another disquieting detail. The brightness along the beams is not uniform. There are subtle pulses, variations so faint that only careful photometric analysis reveals them. They are spaced too regularly to be noise, too coherent to be random, not enough to draw conclusions, but enough to raise eyebrows. Some scientists suggest that these pulses represent clumps of material traveling outward. But the spacing remains consistent over several days, unusual for fragmentation, which tends to produce irregular spacing as mass and velocity vary. In engineered systems, periodic pulses are common. In comet physics, they are not. I let that thought linger, simmering quietly in the back of my mind. Meanwhile, the public starts to take notice. Articles circulate, debates spread. People ask if this could be another Oumuamua, another interstellar visitor behaving badly. And I remember how reluctant the scientific community was to acknowledge the anomalies in that first object. The elongated shape, the lack of a visible tail, the non-gravitational acceleration. Everyone tried to force it into the box of comet, even when it clearly didn't fit. Now here we are again, a few years later, facing another interstellar object that looks even less cooperative. But unlike Oumuamua, whose mysteries deepened because it was observed too late, 3I/ATLAS is giving us new data in real time. And that data is getting harder to ignore. I visualize the beams again. Two straight lines perpendicular to the sun, immune to rotation, immune to pressure, stretching out like structural supports. Nature does not like straight lines. Nature prefers curves, spirals, gradients, diffusion. Straight lines in nature usually hint at something sculpted, something shaped. Even the crystalline structure of minerals has boundaries, not beams stretching 1,000,000 kilometers across space. The sheer scale alone is astonishing. Whatever created these beams, if they are created, operates on a level of precision and stability that seems almost deliberate. Yet I remind myself, deliberate is a dangerous word in physics. Deliberate suggests intent. Intent suggests agency. And agency invites speculation that can cloud observation. So I choose caution. I focus on what we know, not what we fear or hope. The beams are too straight, too stable, too perpendicular. That is the truth that refuses to fade. If they are jets, they violate rotation. If they are dust streams, they violate solar pressure. If they are fragments, they violate probabilities. And if they are something else, something we have not yet defined, then 3I/ATLAS is not just a visitor. It is a messenger of our own scientific limitations. As I close the data set once more, I can feel the weight of the anomaly pressing against the edges of our understanding. And I know that whatever comes next, whether resolution or revelation, the universe has once again reminded us that certainty is an illusion, and the frontier is much closer than we think. When the next week's observations arrive, I can sense the unease settling across the scientific community like a cold mist. The beams are still there, straight, perpendicular, disturbingly unchanged. And with each new image, the sense of an unanswered question grows sharper, more intrusive, like a whisper repeating the same line. This should not be happening. But the universe doesn't care what should or shouldn't happen. It only presents what is. And what is defies the very physics we built to understand these objects. I examine the brightness profiles again, looking for diffusion. Dust should disperse. A fragment stream should widen. Even a stable material should show variance over time. But the beams remain narrow, almost unnaturally disciplined. Their edges don't fray. Their boundaries don't collapse. And the minor oscillations, those faint pulses we detected earlier, now appear more rhythmic, like a heartbeat echoing across the void. Natural systems pulse irregularly. Jets sputter, flare, weaken. But these pulses feel measured, nearly periodic, as if something were regulating the flow. I hesitate, forcing myself to breathe. Physics is a discipline of restraint. You do not jump to conclusions. You do not surrender to the temptation of mystery. But as I run the Fourier transform on the intensity variations, the regularity becomes undeniable. Not perfect, but far too ordered for random fragmentation. Whatever is happening along those beams, it is not noise. Meanwhile, more astronomers join the debate. Some propose exotic outgassing buried deep in the core, escaping through geometrically aligned fractures. But fractures do not respect celestial geometry. They form chaotically, they broaden, they twist. To maintain two perfectly linear vents over such distances, the comet would need internal rigidity that simply cannot exist in a loosely bound icy rubble pile. And even if it did, rotation would still twist the jets. Rotation is a tyrant. It permits no exceptions. But 3I/ATLAS behaves as if it's exempt from tyranny. I plot the body's spin axis again. If the beams were aligned with the rotation axis, that could provide a sliver of salvation. No bending, no twisting. But they are not. They are offset. The orientation argument doesn't save us. It only tightens the paradox. At this point, some researchers quietly revive an old idea. Maybe the beams aren't emissions at all. Maybe they're independent objects, solid bodies moving in synchrony. If two small fragments were ejected with near identical velocities, they would trace straight paths initially. But over 1,000,000 kilometers, solar wind, gravitational shear, micrometeor impacts, radiation pressure, all of these would disrupt the symmetry. For them to maintain coherence, they would require either active stabilization or a mass-to-area ratio much higher than any natural fragment of this size. Natural fragments tumble, they wobble, they scatter. These do not. As I stare at the simulation results, a strange duality forms in my mind. If I treat the beams as fragments, the model collapses. If I treat them as jets, the model collapses. But if I treat them as trajectories, paths of controlled motion, the model suddenly behaves. Velocities align, orientation stabilizes, persistence becomes plausible. But that explanation drags us onto thin ice, into territory where physics meets speculation. And speculation, if left unchecked, becomes mythology disguised as science. Still, data demands honesty. I imagine a scenario, a parent object releasing two small probes or components, ejecting them sideways relative to solar influence. Their paths would appear as long linear streaks in long exposure images. Their trajectories would remain stable. Their velocities could match the observed 500 meters per second. In this interpretation, 3I/ATLAS resembles less a comet and more a node, an origin point for vector lines intentionally cast into space. But I force myself to step back. This is only one possibility, and possibilities are not conclusions. I return to what we can measure. The intensity along the beams has remained remarkably consistent for over a week. No significant fading, no broadening, no irregular scattering. They act almost like filaments under tension, a metaphor that troubles me more than I'd like. Nature does not tension structures across 1,000,000 kilometers, but engineered phenomena sometimes do. The more we analyze, the more cornered comet physics feels. It's like watching a structure buckle under stress. Every assumption we lean on snaps in sequence. Cohesion breaks first, orientation breaks next, rotation breaks last. 3 pillars gone, and once they fall, the entire model becomes untenable. Some colleagues cling to exotic explanations, crystalline ice that fractures with laser-like precision, deep jets shaped by resonant cavities within the nucleus, a complex dance of electrostatic forces. But each idea requires a miracle nested inside another miracle. And science does not run on miracles. It runs on patterns, consistent, repeatable, measurable patterns. And that's the part that unnerves me. The beams are consistent, repeatable, measurable, but not in a way that fits any natural model. Late at night, I replay the newest frames again. The beams stretch across the black canvas like two strokes drawn by an unseen hand, unwavering against the solar wind. They look less like debris and more like intention, and I feel the uncomfortable truth pressing in. If nature is doing this, it is using tools we have never seen. And if something else is doing this, then we are standing at the edge of a revelation our species has never confronted. But I quiet that thought. Curiosity must not be chained by fear or fantasy. It must move forward, one measurement at a time. Still, the mystery remains. Two beams, impossible in shape, impossible in direction, impossible in origin, still pointing horizontally across space, as if marking a boundary we have not yet recognized. And with every passing day, the question grows louder, heavier, more insistent. If this is nature, why is it so perfect? And if it is not nature, then what or who is drawing those lines across the stars? When the most recent observations arrive, I can feel before even opening the data that this will be the moment I have to confront the question I've been circling since the first image. The beams are still there, still straight, still perpendicular, still resistant to every form of physical pressure we know. They have outlasted every prediction of natural decay. They have held their shape through rotation, through solar wind, through distance that should have torn them apart. And they now force us into the final phase of the scientific process, accepting that the old explanations no longer hold.